So here's another example of solving a differential equation. It's the first order and first degree. And we're looking at equations in particular that can be solved by separation of variables. So we're given this equation here and asked to solve that. So we recall that when we have an equation of the form where we have a function of x times a function of y dx and a function of x times a function of y dy, that by inspection we hope to find a term in x and y that we could consider as an integrating factor, that when we multiply the original equation through, it should reduce the equation down to an equation in this form. And you see the importance of this equation is that the first term is all in x, the second term is all in y. And when we can get it in this form, then we usually can solve it fairly easily. So for this equation, first we want to just do some rearranging to get it in the form we're looking for. So just did some algebraic modifications here from this original equation. Didn't change anything, just moved things around. And so you can see now we have this in the general form that we were looking for. This matches that, so we should be able to apply separation of variables to this equation. So that being the case, we can now define our function in x and function in y that we will utilize to create the integrating factor. So in this case, our function of x was the x squared minus 4x, and our function of y was just y. So 1 over the product of those two gives us our integrating factor, such that when we do multiply through the equation with this integrating factor, it reduces it to this form. So this is the form we're looking for, right? Everything in the first term is all in terms of x. Everything in the second term is all in terms of y. So this is what the meaning of separation of variables is. We are able to do that here. So now that we have our equation in this form, we can do some additional algebraic manipulation, which will make this a little easier to integrate. So in this case, the term that's in x, we can use partial fraction separation here, and just a simple algebraic technique that should be familiar. And when we do that, we are able to rewrite the first term then in terms of into two separate terms that should be easier to integrate, which we'll see on the next slide. So here we have the equation we started with, and if we want to use the results from the previous slide, you can see we could substitute in for our x term here, and now we have this in a form that should be much easier to integrate. Then we can do it term by term now. So let's see how that's done. So here we would just, first thing we can do though before we do that is we can multiply through by 4 and then integrate directly by term. So this would clean up the fractions a little bit. And so what this would look like then is the first term in x, you can see as we multiply it by 4, it gets rid of the 1/4 in the numerator. Multiplying the second term by 4 just puts a 4 in the numerator, and 0 times 4 is 0. So this cleans things up a little bit and makes the integration a little easier. So applying the integration to each term directly should yield the following. So it's basically every term there is going to end up being a natural log function. And so the constant we express as a natural log as well for convenience, because we're going to do some combining using some of the rules of natural logs, and we'll see what that looks like. So here we can combine the terms and natural logs, and so we get this in this form. Now we can simply just take the exponential of each side, and that gets us to our final answer. So this is the general solution for the differential equation at the top.